Okay, so back again, and we have our last lecture of the semester right here. And I decided I was tired of looking at PowerPoint slides and talking over them and using that terrible drawing tool that they have. So here we are on graph paper, and you have to put up with lower quality images like this this portrait of Louis de Broglie that I drew for you. But I think hopefully the point comes across nice and clear, and it'll give me a little break from that mode of instruction. So, Louis de Broglie is particularly famous because, one, he won the Nobel Prize in 1929. Okay, oh, that's not, there we go, 1929 Nobel Prize. And he won it for postulating in his 1924 PhD dissertation, for postulating that all matter had a wave-like nature. Okay? So just so you have a frame of reference, some of the fundamentals of quantum theory had been worked out at this point. Let's see, Schrodinger's equation, which we haven't gotten a chance to talk about, sadly, was kicking around. And the photoelectric effect had been observed and explained by Einstein. And yeah, there's been a lot of work going on. But at this point, no one had really solidified the idea that in addition to things like light having particle-like nature, things like electrons, they didn't solidify the idea that things like electrons, little bits of matter, also had wave-like properties. Okay, so he postulated it. So he wrote a theory that made this link between bits of matter like electrons and the idea that they had wave-like properties, wavelengths and all of that kind of thing. So in 1924 he did that, and then experimentally a little while down the road, so 3 years. You usually have to wait longer than that as a theorist in physics to have your theory confirmed, but not in the case of Louis de Broglie. The Davison and Germer experiment, I believe that's what their name was. Yeah. They fired a bunch of electrons at a metallic surface, and then they looked at the reflections from that surface. So the idea is sort of this. They took, so Davison and Germer. So they experiment. And what they did is they took some electrons like this, and they fired them in toward a metal surface. And then they looked at, with a screen over here, at what came out. Now, if they were acting completely like particles, you would expect them to scatter off of this surface and just ping, 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 hit the screen at various points and be done. But what they actually saw is an interference pattern. Not dissimilar to the interference pattern that we saw in our initial discussions of quantum theory when we were talking about the two-slit experiment, which actually came a little later in time than 1929, but is still sort of a nice way of explaining some of the tenets of quantum mechanics. Anyway, they got an interference pattern, sort of these bright and dark lines that are characteristic of the interference of waves, even though they knew that they were starting with electrons and they were detecting electrons. What this did is, as it interacted with this and it bounced off the atomic structure, kind of like X-rays bouncing off the atomic structure of metals and other materials, it had a characteristic diffraction or interference pattern that showed up on the screen and actually revealed some profound things about the atomic structure of this metal film. I think it was cobalt in their original experiment, okay? But you can do it with other things. Okay, so they proved that electrons, so E, have wave-like properties. Okay, and we already knew that. We looked at an application of the fact that electrons have wave-like properties in the electron microscope in the last lecture. So it's not news to us, but at the time, this was a brand new insight, experimentally and theoretically, courtesy of Louis de Broglie and these clever experimentalists. Okay? So though he said a lot more in his PhD dissertation, though he was reasonably concise, there's an equation that goes along with this theory that of de Broglie's that matter, bits of matter like electrons, had a wave-like nature. And that equation is surprisingly simple. It's just that the wavelength is equal to h over p. All right, so what are these things? Well, this is, as usual, the wavelength. And this is, in this case, this would be like the wavelength of the electron, or the proton, or the atom, or whatever little bit of matter we're talking about. And wavelength. Man, the spelling is going. Up here, we've got P. This actually is a symbol that we ran into right at the beginning of the course. This is momentum. And it's equal to mass times velocity. Okay, remember that? P equals mv. And then this, H, is a constant named after one of the famous guys in early quantum theory around the turn of the century between 19th and 20th, that is. Max Planck, it's called Planck's constant, and that's equal to 6.626 times 10 to the negative 34 joule seconds. Okay, so energy and time units multiplied there. That's Planck, the Planck's constant. So lambda h over p. Okay, so you take whatever bit of matter you like, and if you know the constant, which we do, and you know its momentum, which generally we can measure, we can figure out what its effective wavelength would be. So like the wavelength of these electrons, and the wavelength of a proton, the wavelength of an atom, the wavelength of a baseball, the wavelength of you, okay? Just put in the required quantities, and you get out a wavelength. So, what does this tell us about quantum objects and bits of matter in general? Well, it appears to tell us that even we have wave functions, and indeed we do, and we have wavelengths, and so we could do all the spooky things that quantum theory says we should be able to do, which is like, I don't know, go through both slits of the two-slit experiment at the same time and create an interference pattern on a wall. Seems a little weird for, like, I don't know, baseballs instead of electrons. So let's investigate this a little bit further. What is it telling us literally that we all live in this world of quantum theory and we should be seeing things of this nature, of these odd and mysterious nature, happen all the time? Or is it telling us something a little bit more comporting with reality? And fortunately, it's the latter of those. Let's do a couple of quick calculations. So let's do wavelength of the electron. So we'll say it like that. Okay. And, oh, sorry, just remove that from the pen and paper so I can get it in there a little more easily. All right, and then we have up top the H, right, this Planck's constant. And below we have the mass of an electron, which is 9.11 times 10 to the negative 31 kilograms. Oof, tiny. And the velocity of the electron. Now, of course, it could be very slow or it could be very fast, but let's pick a velocity that is roughly in line with some of the fancy electron microscopes that we were talking about. And if you accelerate an electron with the kind of voltage that you were accelerating electrons with in those electron microscopes, well, you get about 1.9 times 10 to the 8th meters per second for its velocity. Colossal. Significant fraction of the speed of light, you'll note. You know, maybe almost 2/3 of the speed of light. So, if you do that calculation, punch them all into your calculator. I'll give you a second. You want to erase me? 4.9 times 10 to the negative Okay. 12th meters, right? Because we have meters for wavelength. Okay. Well, oh, I'm sorry. This is 3.8. Okay. 3.8 times 10 to the negative 12th meters. Okay, well, that seems quite small. What is this telling us? Well, an atom, for instance, typical atom, has a diameter of about 10 to the negative 10th meters. So this wavelength of the electron is about 100 times smaller than that, okay? But isn't anywhere close to, like, I don't know, the diameter of, get to this later, okay? The diameter of a nucleus, which is 10 to the negative 14th or 15th, depending, okay? So, seems reasonable for an electron, which is a constituent of an atom. Okay, that's not very exciting. We kind of suspected it might work out to be something like that. But let's look at the wavelength of a baseball. You know, something we might toss around. Ooh, move up my paper. There we go. All right, so we put in all the same stuff, right? For up here, that's Planck's constant. It's always the same. The mass of a baseball, something like that, would be, you know, well, actually, yeah, I've got the mass of a soccer ball written down over here, so let's go soccer ball, okay? And then that's just under half a kilogram. Multiply that by, let's say someone gave it a pretty good kick, and so it's going 30 meters per second, let's say. All right. Plug all that into your calculator, and I think if I typed it into my calculator correctly, we get 4.9 times 10 to the negative 35 meters. Okay? Even if I'm off a little bit, I think, generally speaking, 10 to the negative 35 is about negative 35 is what you're going to expect to get out of that. What does that tell us? Okay, well, we already knew that electrons were small. They were like this subatomic particle, and their wavelength, according to quantum theory, comes out to be, you know, sort of on that scale, like smaller than an atom, but bigger than a nucleus. This wavelength for a soccer ball, okay, or something, you know, on that scale, moving about that fast, is incredibly small, right? I said that the nuclear diameter, okay, nucleus diameter is, you know, about 10 to the negative 14th meters. So we're talking about a wavelength for our soccer ball that is 21 orders of magnitude smaller. 21. So 21 zeros. I'm not even really sure how to describe how small that is compared to nucleus. I mean, like, there's no physical analog to that kind of distance. Okay, we don't know of anything that is that small, and yet there it is. Okay, so this is actually a good thing though, because if the soccer ball had a wavelength that was like the size of a soccer ball, you'd expect the soccer ball to exhibit a phenomenon that we're going to talk about now, but I wrote down early thinking I might have more space, so let's bring it down here a little bit. You'd be expecting the soccer ball, if it had a wavelength that was sort of like, you know, a quarter of a meter long or something like that, so sort of the size of the soccer ball itself and the things around it, you might expect the soccer ball to exhibit something like quantum tunneling, and you send it against a wall, you're kicking it, you're getting in your practice, and then suddenly, poof, it goes through the wall. Because there's some non-zero possibility, because remember that the position of the soccer ball is something that is dictated by its wave function. And so there's a most probable position, but there's also a probable position, a less probable position, where it actually ends up on the other side of that wall. Crazy, right? Just appears there, or would, if it had that property, okay? Now, that's the essence of quantum tunneling. In other words, you have some object, and it's going towards a barrier. You can think about it as a wall. If you're talking about an electron, you might think about this as like an energy barrier, so it's within the material, and it can't actually get through because it doesn't have enough energy to actually go over the wall. So if it's going to get through it, then it has to quantum tunnel, because classically, you throw the baseball, it hits the wall, it bounces back. Okay? But in the realm of quantum mechanics, when this object, whether it's an electron or some other tiny little quantum thing, has some wave function that describes it, okay? And thus it has a probability when it approaches the wall of having the tail of its little probability distribution be on the other side of that wall. Okay? There's some non-zero chance of when it hits that wall, it just passing right through it and happily moving along its way. Okay? It's weird. If you remember back to those transistors that we were talking about as an application of the one of the consequences of quantum theory, the bandgap in semiconductors. Well, if you go back to that diagram, and actually I can just replicate it here. You've got like the gate material, and you've got this like little insulating barrier, and there's this gate, and then there's the source, and there's the drain, and then there's this channel in between that you can turn on and turn off, so allow electrons to pass through it, or not allow electrons to pass through it by applying a voltage to the gate. Okay? This little insulating gap actually is a barrier for electrons, and yet the thinness of this barrier is so small, like just a few atoms thick in modern transistors on these computer chips, that there's a non-zero chance, and actually a pretty significant one. I mean, it's still like tiny. It's far less than 1%, but you're still talking about electrons able to just be like, well, I'm behind the barrier, I can't get there, and then suddenly, poof, because they have some non-zero probability of moving to the other side of the barrier, they just do. And that's called gate leakage, and it's a big problem for semiconductor companies. They have to manage that whenever they shrink down the transistors enough. And there's lots of tricks you can play to do it, and they've done a good job so far, but it is one of these limiting design factors, and it's all down to quantum mechanics. Now, if we go back to this idea and we think about this not as an electron, but as a soccer ball, well, sure, the soccer ball has a wavelength. It has a wave function, but that wave function is so colossally small. It's much smaller than the soccer ball itself. It's much smaller than the width of the wall. And so you could sit here for the age of the universe and fling your soccer ball or your baseball or yourself or whatever else against a barrier, and you would never go through. Okay? The probability is technically non-zero. Okay? It's not mathematically zero, but it is so unlikely that you are unlikely to ever observe it, and you'd be wasting a lot of time if you went ahead and tried to run that experiment. Okay? And that's what the de Broglie wavelength equation is telling us about that. All right? So, a little bit about quantum tunneling, a little bit about the de Broglie postulate, and de Broglie himself, and this equation that tells us about the wavelength of bits of matter. Okay? And remember that de Broglie is the one that theorized this connection between matter, bits of matter, and the idea that they could have wave-like properties and have a wavelength and a wave function and act like quantum entities. Right? Really profound insight, and one that still has power these days, though the models have gotten more sophisticated. So we're coming up on 20 minutes. I just wanted to say it's been a real pleasure having you all in the course this semester. It's the first time I've taught it, so I'm sorry if it was a little rough around the edges. And then, of course, we had this whole remote learning thing happen, and it's been challenging from my end, and I'm sure even more challenging from your end. Please do get in contact with me as we approach the final. You may be feeling confident if in that case, but drop me a line. Just tell me how your life is going in this new normal. And I hope to see you around in the fall. Fingers crossed that everything goes back to sort of normal by then. And I would also like to say that it's unclear to me whether there will be sort of formal student evaluations of the course and the instructor and all of that kind of stuff this semester. It's a little unclear from the emails that I've gotten whether that would go ahead or whether it would sort of count, quote unquote, and all that kind of stuff. But regardless, I really do want to hear what you have to say about the course. And so maybe I'll just send you a survey of my own if you're not going to be doing evals, official evals, after we're all finished up with the course, and you can give me a few bits of constructive criticism. So I hope you enjoyed this last lecture, quote unquote, and it'll appear on YouTube and Brightspace in the near future. Good luck studying for the final exam. Be looking for more materials on all of that to be appearing online in the very near future. Okay, thanks and goodbye.